So, good evening everyone, this is Obi-Wan Pez for N-Simplex Pachinko. We're off tonight to do some more of the final exam, due to the fact that Matthew and I had a good chat last night, but I didn't end up doing a whole lot of the exam. So but we had a good chat, so this is fun. Okay. So we were looking at number 3 was going to be the next question in the series. Alright, so we want to find all 6 trigonometric functions for the angle whose terminal side goes through the point -7, -4. So when I was doing this with Trig earlier, we said, first of all, pretty much the first thing you always want to do in trigonometry is to draw a picture. And especially when we're talking about trig functions, we're looking at, roughly speaking, a point that goes through here, which is on a larger circle. Which would look something like this. Give or take. Alright, so what we've got then is that this has a and no, you can't use the protractor. Alright, the terminal side goes all the way through -7, -4. And the, oh, nope. Need that back. You'll see why in a minute. Alright, so for the terminal side of this angle, which goes through -7, -4, the angle in question is this angle here, which is in the third quadrant. This is our theta that we're going to be talking about. Now, I did say in some of the trig stuff, this angle down here is our reference angle. This is going to be theta prime. And as it turns out, the sine, cosine, tangent, secant, cosecant, cotangent will all have the same values at theta prime as they do for theta, provided that you remember that theta prime is in the third quadrant. So your calculator, if you just put in this little, like, I guess it turned out to be somewhere around 32-degree angle, it would not come out with exactly the same answers, because 32 degrees is going to be in the first quadrant, everything would be positive. And here in the third quadrant, we know that our sines and cosines, at the very least, are going to be negative. So one way to do this is to remember what your trigonometric functions are and what their side length ratios are going to be. So your sine of theta is going to be y over r, keeping in mind that in this particular case, r is not going to be 1. So this is not on the unit circle. So you can't just say sine of theta equals y, and therefore sine of theta equals -4. That doesn't work, right? The output of the sine function has to be between -1 and +1. That's all you get. So -4 is just way out there. You can't have it. So in this particular case, this ends up being -4 divided by, and now we have to find the r. So our r value here, if you remember the relationship exists, r squared equals x squared plus y squared. Because we can form up a right triangle from the point that we were given, -7, -4, and the fact that these are orthogonal coordinate systems. So these are going at right angles to one another. This distance here is going to be -4, 4 in the negative direction. Wow, I just messed that up. Okay. This is going to be -7. 7 in the negative direction. Our y distance is going to be 4 in the negative direction, or -4. Which means r squared is going to be equal to x squared is -7 squared plus y squared is -4 squared. So r squared is equal to, this is 49 plus 16 is going to be 65. So then r, or rather the absolute value of r, is going to be the square root of 65. However, r is going to be just a scalar, so it is going to be just a distance. It is only the square root of 65. And the square root of 65 itself breaks down into a 13 and a 5, which are both prime factors, so this isn't going anywhere. Can't simplify this at all. So this is going to be -4 over root 65. And I pretty much guarantee that your teacher is not going to allow you to stop here, and you want to rationalize the denominator. I have feelings about this. Personally, I don't think it's that important, especially right now. Rationalizing the denominator was much more important before the advent of digital calculators, where you actually had to find the decimal approximations of fractions. So if you tried to find -4 and divide it by the square root of 65, you'd have some problems. However, if you took both the top and bottom and multiplied by the square root of 65, this gets us -4 square roots of 65 up top, and down bottom, you end up with just 65. Right, root 65 squared is 65. Square root of 65. All right, so when you get this, now you can say, well, it's actually a lot easier to take -4 times the square root of 65, whatever that ends up being, and then dividing by 65. Because 65 is now a 2-digit number, and you don't have to worry about long strings of decimals. The square root of 65, you would. It would be quite gross. I would not want to do that. Alright, the cosine of theta is equal to x over r, which similarly is going to be -7 over the square root of 65. Again, me personally, I tell my students, don't bother rationalizing. We have digital calculators. We can all figure this stuff out. But if it turns out that rationalization makes something kind of nice, that you can, like, divide out stuff or whatever, then maybe it's worth it. Right, if this ended up being a 5 out here, 5 square roots of 65 over 65, then you can divide out a 5 from each one. So that would be nice. In here, though, we don't get that. So, curses. Alright, sine, cosine, tangent. Tangent is going to be y over x, or you could have the sine over the cosine, or whatever you wanted to put in here. Either way, y over x is going to be negative 4 over negative 7, which ends up being 4/7. And it doesn't really matter what order you put these in. Just keep in mind that your teacher might have a specific order. The cotangent of theta is 1 over the tangent of theta, so it's x over y, which is then going to be the reciprocal of these numbers, so it's going to end up being 7/4. All right, so I am here. All right, anyway. So the secant of theta is going to be, you could again argue what you want here. I'm going to put r over x to keep it consistent with what we've got going. It is also 1 over the cosine of theta. Which one would you rather reciprocate, by the way? I hope you answered this one, because that is so much easier to reciprocate. You end up with a rational denominator in the first place, so then you don't have to worry about whether or not to rationalize stuff. So this is going to be square root of 65 over negative 7. Or just negative square root of 65 over 7. You could decide where to put the negative sign. That's fine. It's all good. How about the cosecant of theta? Again, here, this is r over y, or 1 over the sine of theta. And again, we can reciprocate this number here. It keeps it nice. This is going to be the square root of 65 divided by negative 4. And we already got the cotangent. So that is all 6 trigonometric functions. All right, what does this test? Well, it tests the very basics of, do you understand trigonometry? Do you understand how it all fits together? If you get stuff like, you didn't rationalize something, you still got trig. Okay, don't worry too much about it if your teacher marks you off a point or two because you forgot to rationalize stuff. It's fine. You'll be fine. If you get a couple of these mixed up, or especially if you get your sine and cosine mixed up as horizontal and vertical, or if you're plotting this as this is your y and this is your x, that's a big problem. So that is an Algebra 1 issue that you should get that fixed very quickly. So go on to Khan Academy or some other learning management system and figure this stuff out, because you're going to want to get this done before school starts up again. Or if you're still in school, you're going to want to get this figured out before finals. Yeah, I had some students who mixed up X and Y and everything, and it ended up being, like half credit, because all right, if you want my opinion on how to draw all this stuff, remember that we have a large diagram that you can draw out of the unit circle, or in this particular case, in this particular case, it won't be a unit circle, it'll be a much larger circle. Radius approximately 8, give or take. I don't exactly know what it is, but it's big. So our individual trigonometric functions actually have physical values on the circle to help you find what they are and what they mean. So this right here, this distance, is actually the tangent to the circle on the side. So the tangent to the circle here on a unit circle is going to be the tangent of theta. If we scale this up to a radius r, or in fact scale it down to a radius r circle, then this will be r tangent theta. Now, if you're wondering why that is, why is it going to be r tangent theta? This is because you can make similar triangles here. So we have the tangent of theta, or the thing we don't know yet here, its vertical value. We have our r value here is the hypotenuse. We have our horizontal values and our vertical values, which we'll be able to use for this. You could scale this specifically from the unit circle up to whatever we have here. So in this particular case, right, this is going to end up being all right, our angles are the same. You got right triangles, and our theta is the same here. Therefore, both of these must also be the complement of theta. So 90 minus theta for both of those. So they have to be the same angle. If we wanted to, we could label this as 1. This is our x and y normalized down to the unit circle. And then here we have actual values going all the way out to the tangent. Alternatively, we could instead of x, y, and 1, we could actually use the tangent of theta triangle here from the unit circle versus this one from this one here. So we have here that this is r and this is r. This little one here would be the tangent of theta, and this little one here would be 1. Should be all we need, right? Yeah. So we want to know what this is here. So this is saying we need to relate the sides. This is what our question mark is divided by the tangent of theta is going to be equal to big over small r over 1. Big over small. And then here our question mark is going to be equal to r tangent theta. That took me longer than I wanted, sorry. But the idea here is that we're just going to get similar triangles for the unit circle and then blown back up to this full size one here. All right. So here in this triangle we have r tangent theta is going to be the vertical value here. This right here is going to be r sine theta. So it's going to be r cosine theta. This is going to be r times 1. And on the big triangle, again, we have here, this is r, or the square root of 65. Nuts. And here, to that point, we have this is the secant of theta, again, scaled up to a radius of r. And then on the other side, we have the r cotangent of theta. And r times the cosecant of theta. If you know your diagram, you could also come out with these values as well. All you would need is, again, your x, y, and r values, and then you could be able to do similar triangles with all of this. Do I recommend that on an exam? No, not at all. But so I don't recommend it on an exam, but if you're kind of stuck and you don't know exactly what's going on, this might be a good way to, at the very least, get a couple of points for, like, you know, I know what these things are, I just don't know how to find it. And again, my students were given a full 8.5 by 11 sheet of paper. They could fill one side with whatever they wanted. There's a lot of stuff in Trig, so we cut them a little break. All right, so we found all 6 of the trigonometric functions, given criteria. I am scoring this out of 7 points, 1 for the diagram and 1 for each of the 6 trigonometric functions. Points awarded, partial credit if it warrants, but generally it's pretty cut and dry for that one. All right. 4. Solve. Give exact simplified values for all valid solutions. So this is also an important caveat. All valid solutions. Not all solutions are necessarily going to be valid. Some of them will be extraneous, and you will need to figure that out pretty quick. Again, I'm hoping that people will have studied hard enough that they would know an extraneous solution, or at least know how to find an extraneous solution pretty quickly. One thing that you could do is just look on your calculator and figure out, are there any intersection points? Look on Desmos or whatever. Obviously, if you're not allowed internet resources, you can't do that. But if you're just doing stuff at home or whatever, one option would be go on to Desmos, plug in each of your equations separately, and then figure out where there's a solution by looking at where the 2 graphs intersect. In this particular case, they end up intersecting, or both of the exponential functions are traveling this way, and then the lower one, 5 to the x minus 3, is going to catch up eventually, having a larger base and all that. So with this, there are several different ways that you could go at this. It's up to you which way you want to do it, but some people have chosen log base 3. Which is perfectly valid for this, and in fact for any log. It doesn't actually matter which log you're finding here. So even if I went, let's say, I went at this and said, let's just do log base b. So literally keeping it generic. What we would get here is that our exponents come down in front. So we get x plus 1. Log base b of 3 is equal to x minus 3, parentheses, log base b of 5. A lot of students get stuck here or don't know what to do, or they start panicking or whatever. The important thing is that you recognize that there are x's and there are not x's. All right, and in algebra, what do? You get all the x's to one side, you get all the non-x's to the other. So here you're going to have to distribute in order to get rid of it. So this is going to be x log base b of 3 plus log base b of 3 equals x log base b of 5 minus 3 log base b of 5. Right, and we can make this more positive if we make this one go that way and this one go that way. At least it'll look more positive for the moment. So this is going to be a 3 log base b of 5 plus log base b of 3 is equal to x log base b of 5 minus x log base b of 3. Factor out an x from both of these. This is x times log base b of 5 minus log base b of 3. That's fine. And this over here can just stay as is. 3 log base b of 5 plus log base b of 3. So that means that x here we're going to divide. 3 log base b of 5 plus log base b of 3 divided by everything over here. Log base b of 5 minus log base b of 3. Now, to some of you, that may not be a very satisfying solution, and that's fine. Doesn't have to be. But if you insist, right, we could also do this specifically with any log that we want. So do it with log base 5, and your log base b's of 5 now become log base 5 of 5, which is 1. So then up top we end up with a 3 plus log base 5 of 3 divided by 1 minus log base 5 of 3. If we did log base 3 instead, this would be 3 log base 3 of 5 plus log base 3 of 3, which is 1. And then log base 3 of 5 minus log base 3 of 3 is minus 1. If you wanted to do this from the beginning using natural log, because quite frankly it's much easier to draw a natural log, then that's fine too. I would have said, for instance, that this was the natural log of 3 raised to the x plus 1 equals the natural log of 5 to the x minus 3. This is x plus 1, natural log 3 equals x minus 3, natural log 5. This goes through the same stuff, so x natural log 3 plus natural log 3 equals x natural log 5 minus 3 natural log 5. Oops. You know what it is anyway. And if we shift materials around, we get, again, 3 natural log of 5 plus natural log 3 is equal to x times the quantity natural log of 5 minus natural log of 3. X is therefore 3 natural log 5 plus natural log 3 divided by natural log 5 minus natural log 3. I much prefer using natural log just because it's easier to flick my wrist and get natural log out of it than to write log base whatever. Just ends up being such a pain. Who has time? Alright, divided by natural log 5 minus natural log 3. Yeah. So x is about 11.6026. Alright, I scored this a 6-pointer. And again, I'm looking for, do they go through all the individual steps correctly? The major log properties, are they bringing down the exponent? Are they then, if they combine any terms, are they combining them correctly? Because you can also combine this correctly. by saying that the, let's go with this one. The 3 natural log 5 is the same as the natural log of 125 plus natural log of 3 divided by natural log of 5 minus natural log of 3. And then up top, this is a product. Right, this is going to be natural log of 5 raised to the 3rd power. And then here we're going to multiply because we're taking our natural logs and adding them together. So natural log of 375 divided by the natural log of parentheses 5/3. If we're going to do the same thing. One of my students also noticed at this point that this was just the change of base formula. So this is the log with base 5/3 of 375. Now me personally, I said, why did you do that? Because that's a nightmare. Why would you want to? But good news, it comes out to the exact same value. So it doesn't really matter whether they found it using change of base formula and all this or not. Right? It yields the same 11.6026, etc. And it is mathematically sound. They just had to do a lot more work to get there. Now, in my exam, I actually gave them all of the terms of the sequence. So there are a grand total of 10. And I listed all of them out. So if you remember, this is sigma notation. It needs to look like this. We need to have the terms listed in here in explicit form. We also need to then index as we go from I equals 1 to however many terms there will be. So I just gave it to you. There are 10 terms. It's got to be indexed from 1 to 10. Now you could, in theory, index it on some other numbers, and that's fine. But again, I don't really recommend that. In this particular case, as I goes from 1 to 10, we have a sub I is again the term that's represented here. So a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, 6, 7, 8, 9, and 10. We need to make sure that we're seeing the pattern here. So as we go from 720 to 707, and 707 to 694, and 694 to 681, and from 681 to 668, etc., 616 to 603, we're always subtracting by 13. So this is a linear function. Right, we are going to subtract this value as we keep going across. So if it's a linear function, that means that you can find the slope, which we already have. It's negative 13 for every one term that we go over. And we start at 720, which is term number 1. So if you remember your arithmetic sequence, you could say that this is going to be a sub 1 plus d times I minus 1. In this particular case, this would be a sum. I goes from 1. I goes from 1 to 10 of, this is going to be 720 minus 13 times I minus 1, like that. That's it. That is all you need to find. And if you want to put that this is the 10th partial sum by putting s sub 10, then you can do that too. It's fine. It doesn't really matter in this particular case. All right. If you don't like this, this is perfectly fine because it doesn't actually matter. You don't necessarily have to take the first term. This could in fact be a sub k plus d times I minus k, where k is any term that you want to pick. So you want to figure out what this is in terms of the 9th term, that's fine. You could do that. This ends up being 616 minus 13 times I minus 9. You could do that too. You could in fact use a sub 0 plus d times I, a standard linear function. And this one would have been, let's see, add 13 more, so 733 minus 13i. Right, in order to get to the first term, you have to do your first subtraction and get it down to 720. All that's perfectly valid. This works. All right, now I did say part A. Part B, find the sum of the first 100 terms in the above sequence. So if you had this thing starting from 720 and counting down 13 every time, we've only got the first 10 that were listed up top. I want the first 100, and now sum them all up. Now from class, this is the Gaussian method, or there are other people who actually discovered it before Gauss. However, he discovered it when he was a schoolboy, independently of anybody else, so, Okay, so the sum of the first n terms of an arithmetic sequence, which means we are constantly adding the same amount every time, is that we're going to take the n value, the number of terms we're trying to find, multiply it by a sub 1 plus a sub n, the last term, first plus last, and divide by 2. This can be seen in a number of different ways. The way that Gauss did it was that he split the the numbers 1 through 100, and was able to basically just wrap them around and then add all the way down the list. And what he ended up getting was that he was taking the first and the last term, and the second and the second to last term, and the third and the third to last term, and they were all summing up to the exact same value. And then he was multiplying by n over 2, because half of the list had been folded over onto the other half. So you only have to find half as many. If you don't like that one, that's fine. You don't have to necessarily do that. You could, in fact, duplicate the number line. So create the sequence that you're trying to sum up, and then invert it and put it underneath the other one, and then add all those terms. And again, you're going to get the exact same value. A sub 1 plus a sub n will be the same as all the rest of the sums. Guaranteed. And then, since you're finding the sum of all of these, then you've got two sequences that are lined up next to each other, so divide by 2. My other favorite way to look at this is an average. A sub 1 plus a sub n divided by 2 gets you the average value of all the numbers in the entire sequence, and then you're multiplying by the number of terms that there are. Really like it. All right, s sub 100 is equal to 100 times a sub 1 was 720 plus a sub n is going to be, we take this and we say, okay, this is going to be 700. Let's do the other one. 733 minus 13 times 100. 1300 off of 733, or subtract the other way, is going to be 600 minus 33 is 567. Sure hope that's right. Anyway, yeah. So that's going to be a negative 567 due to the fact that, again, this was actually negative 1300 plus. But anyway, and then divide by 2. So 720 minus 567 is going to be a 100. That's what I get for doing it this way. All right, so all right, 7 off of 20 is going to get us 13. This is a 56 out of 71 is going to be a 15. So 153. Yeah, cool. So this is going to be a 100 times a 153, and then divide by 2. So this is going to be 15,300 times 100. Or sorry, 15,300. All divided by 2. So that's 7,500 and 150. So 7650. I score this as a 4-pointer for the first part, so find the sequence, and then a 3-pointer for the sum afterward. 2 points for, or 1 point for the actual formula, 1 point for plugging everything in, and 1 point for the solution. And work being part of both of those. All right, 6. Find the equation with zeros, -4, 0, with multiplicity 2, -1, 0, with multiplicity 1, 1, 0, multiplicity 1, and it goes through 215. For me, keep it in factored form. For your teacher, your mileage may vary and all that good stuff. So if this thing has zeros, -4, 0, -1, 0, and 1, 0, then in each of these particular cases, our x value is equal to -4, -1, and 1. And the actual zeros for these things then become x plus 4 equals 0, x plus 1 equals 0, and x minus 1 equals 0. It is a hard fact that you can multiply together anything that is equal to 0 and it still becomes 0. So realistically this is an OR statement between them, but the fact that it is an OR statement allows us to say, okay, again, if any one of them is 0, then the whole product is going to be 0. So x plus 4, x plus 1, x minus 1. What does this multiplicity thing mean? Well, multiplicity says that how many times is this 0 going to show up in the full equation? So here, x plus 4 is going to show up twice with a multiplicity of 2. The rest have a multiplicity of 1, so this is it. Then this is all equal to 0 on the other side. Again, if any one of them is 0, this whole product is 0. And it doesn't matter what we multiply by. So I can multiply by some sort of constant on both sides, and it's not going to change the overall function. If I add or subtract anything, that is going to mess up everything. So you are not allowed to, at all, change anything by addition, because then our zeros shift out or in or whatever. They'll change. But if you multiply by a constant, it doesn't change these zeros. Right? We still can say if any one of these things is 0, then the whole product is. Okay, 0 times a is just still going to be 0, so that's not going to change anything. Then this becomes the equation generally for the function we're looking for. So f of x is equal to, let's do p of x just because, right, polynomial, a times x plus 4 squared times x plus 1 times x minus 1. Then we say, well, this whole thing needs to go through this point, 215. That's the only other piece of information we have. So p of x is going to now become p of 2, x value of 2, y value is 15. And that is set equal to a times the quantity, 2 plus 4, parentheses squared, times 2 plus 1, times 2 minus 1. This says then that 15 is equal to a times 2 plus 4 is 6, squared is 36, 2 plus 1 is 3, 2 minus 1 is 1. 3 times 36 is 108, and we can divide on both sides here. So a is going to be equal to 15 over 108, or we could have left it in factored form and said very simply the 3 will divide out from both pieces. So we'll be left with a 5 up top and a 36 on the bottom. So therefore, using this and this here, our p of x must be equal to, if it is a polynomial in, 100% a polynomial. Probably should have said this is a polynomial equation. Find the polynomial equation with zeros. Yep, anyway. 536 times x plus 4 squared times x plus 1 times x minus 1. Alright, that is our equation for this particular polynomial. I'm setting this as a 6. I'm going to say probably up until they get this part right here, that's going to be 4 points. So all the work making sure they have all the zeros in the proper multiplicity, it's going to be 4. And then finding a and putting it all back in here is going to be your last 2. All right, 7. Solve the following inequality using exact values. log base 3 of x plus 3 minus log base 3 of x squared minus 1 greater than or equal to 1. All right, right out of the gate here. Everybody who's taken precalculus should immediately have red flags going up. This is going to have some domain issues, which are going to prevent us from getting possible answers in certain regions. So, we have to look at this and say, what do we know about logarithms? Well, the argument to logarithms, so here x plus 3, and here x squared minus 1, must be positive numbers. They can't be 0, they can't be negative. So x plus 3 must be strictly greater than 0, intersected with, because this also has to be true, x squared minus 1 must be strictly greater than 0. So here x must be greater than negative 3, intersected with x squared greater than 1 if you take the square root of both sides. This is really important also. You cannot just say that x is going to be greater than the square root of 1 is 1, right? Because that completely eliminates one possibility, and that is that you have a large negative number in here. So this is the absolute value of x is greater than 1. So what does this mean? This means that x must be less than negative 1, or x must be greater than positive 1. Intersected with, or and, x must be greater than negative 3. So what does that take for us? Well, this means that we're going to have a number line. X must be greater than negative 3. And we have negative 1 and positive 1 as the other possibilities here. So we have x must be greater than negative 3, and either x must be less than negative 1 or greater than positive 1. So where do those lower ones intersect with the upper one? That's going to be this region here and this region here. From negative 3 to negative 1, and also from 1 off to infinity. All right, now this is not the answers. This was just our, like, legal domain. Where are we allowed to have answers? Of course I put it there. So, we are allowed to have answers between negative 3 and negative 1, or above positive 1. So how do we figure this out then? Well, this is where we fall back on all of our log stuff. If we're just doing operations on the left-hand side or just on the right-hand side, nothing really changes in terms of the inequality. So you can, in fact, rewrite this as the log base 3 of x plus 3 divided by x squared minus 1 is greater than or equal to 1. From earlier, 1 is the same as log base 3 of 3. All right, one of the things that you can do, and this is a strategy I kind of like, is kind of ignore the greater than symbol for the moment and just try to find the solutions. once you try to find the solutions to the equation of these things, then you can look for test values on a number line like this. So if you say that this is, pretend that it's equal, this is going to be the same as x plus 3 over x squared minus 1 is going to be asterisk equal to. It's not really equal to, but again, we're just trying to find border solutions. So where do these values change over? It's going to be equal to 3. So here, this is a classic example of using these one-to-one functions. So a log base 3 is a one-to-one function. If the log functions themselves are going to be have a certain relationship, then the interiors to those logs will have the same relationship. So here, if we're just looking for border points, I just go with equality. Say, look for when they're going to strike each other. Here, we're going to multiply both sides. This becomes x plus 3 is, pretend, equal to 3 times x squared minus 1. 3x squared minus 3 is equal to x plus 3. Subtract x, subtract 3. And this becomes 0 is equal to 3x squared minus x minus 6. How do we solve this quadratic? Well, you can use the quadratic formula. You can try to factor it. This is 18 with a difference of 1. So yeah, not going to happen. So x is equal to negative b is negative 1 plus or minus the square root of negative 1 squared minus 4 times 3 times negative 6. Two times 3. X equals 1 plus or minus the square root of 1 plus now 72 divided by 6. 1 plus or minus the square root of 73 all over 6. It's going to be our possible solutions for this. So now we just have a series of individual points that we can check versus our domain. So negative 3, negative 1, 1. We know that this is going to be our domain. Now we want to check again, where are these points? So 1 plus root 73 divided by 6. Versus 1 minus. This is 1 minus root 73 over 6, which is about negative 1.26. And the positive version is 1.59. 1 plus the square root of 73, all divided by 6, which is about 1.59. All right, these are all approximations. So we're going to get something. Again, we now have to check test values and say, what kinds of test values do we want? Well, we don't need anything out in this region at all, nor anything in this region here. All right, we can't have values there. So here, let's pick a negative 2 as a test value, negative 1.1 as a test value, 1.3, and 2, positive 2. So we need all of those test values to be had. And again, I tell my students, just plug them in, see what you're going to get for this particular stuff. So say in the graph, I had no, that's unfortunate. Took out the other. I took out number 9 here that was in my calculator. I'll come back to it later, I guess. All right, so in the TI calculators, it's pretty convenient. You can actually just find the Y1 you can find the Y1 variable, which is where your equation is plugged in, and then use it like function notation. So do like Y1 parentheses, so Y1 of, and then plug in your individual values. So I'm doing Y1 of -2 is getting us a -1. I shouldn't do that. It's getting us a -1 is greater than or equal to 1. Right, the entire left side here, I ended up getting that when you plug in -2, you end up with a -1 value. And is that greater than or equal to 1? Well, that makes a false statement, so no. When you plug in, -1.1, you end up with a 2.0048, which is greater than or equal to 1. True. So this region is going to be allowed. If we plug in 1.3, then we end up with 1.665 greater than or equal to 1, which is, again, a true statement. And when we plug in 2, we end up with a 0.4649 greater than or equal to 1, which is a false statement. So this is going to get this region here, and this region here. We are not allowed to have values at these points, which from a different perspective, these are asymptotes. So we're going to have open circle at 1 and -1. And these are forbidden values from our log base 3 of x squared minus 1. And then at these values, these were the values where we found they are equal to 1. So if you actually plug those in, you would get a 1 value back. And we said that this log stuff must be greater than or equal to 1. So those are valid values. So these are going to be solid points. So then the solution to this is going to be x must be between our bracket 1 minus root 73 over 6 by -1 open union with open 1 with 1 plus root 73 all over 6 bracket. All right, number 8. I've already asked this as part of several of the previous questions. However, this is more explicit. I'm asking you directly, right? Find the domain of this particular function. F of x is equal to the fourth root of 9 minus x squared divided by the natural log of x. All right, now this particular one becomes rather interesting because we've got a couple of problems that exist. First of all, this is a fourth degree polynomial, this is a fourth root, so all the stuff on the inside of the radical must be non-negative. So 9 minus x squared must be greater than or equal to 0. That's okay. Second of all, the natural log says that x must be positive, strictly positive, can't be 0 itself. And there is one other thing that really is important. The natural log of x cannot be equal to 0. This is something that even I forgot, so I would have to go back and potentially grade all of my students' exams again, because I screwed up this one little thing. I forgot that this is also a problem. One of my students, unfortunately, one of the last ones that I corrected, pointed this out on the exam, and I went, oh no, that's a lot of other people who are going to lose points. But yeah, good for them, I guess, that I didn't go back. End of the semester gift, if you will. And this is the intersection between all of these. All these things must be true simultaneously. So with this one, we've got now 9 is greater than or equal to x squared. Here we still have x is greater than 0, so that's easy enough. And here, if you take the inverse operations here, natural log is e. Right, e raised to the natural log of x cannot be equal to e raised to the 0. E to the natural log of x just is x. These are inverse operations of each other. X cannot be equal to e to the 0, which is 1. Here, you could, again, take the square root of both sides. This is going to be the absolute value of x must be less than or equal to the square root of 9 is 3. So the absolute value of x being less than or equal to 3 would allow for any values between -3 and +3 inclusive. However, x cannot be 1. And also, x must be greater than 0. So when we take all three of these into account, this is only going to allow us with from 0 up to 1, but 1 has to be empty, and then from 1 up to infinity. Oh, no. Jeez. And then 1 up to only 3. There we go. So the domain of f is going to be such that x must be from 0 to 1, union with all open, 1 open up to 3 closed. All right, number 9. G of x is equal to 45x to the fourth plus 192x cubed plus 41x squared minus 30x minus 8. All right, this is find all zeros of this function by hand. So in terms of by hand, what I did in my class was that I am allowing them to use their graphing calculators to estimate where the zeros are, where they think the zeros are. They then must prove that those are zeros by way of factorization. So, how do you factorize this thing? I gotta tell you right now, it is not the way that photomath shows you. Okay? Don't do that. Don't do it. Don't do it. So, plug this into your calculator. Of course, I eliminated it before, so oops. Do it all over again. 192x cubed plus 41x squared minus 30x minus 8. All right, x is -4. Somewhere about -0.5 or -0.5, and it's slightly closer to 0 than a half. Don't know exactly what it is, but it's somewhere in there. And I think it has a multiplicity 2. All right, now how do I tell that? Well, this thing has a parabolic shape as it gets close to x equals -0.5 or whatever it is. Okay, and the other one appears to be close but positive. So, like positive 1/3 to a half. Don't know exactly what it is, but we'll figure it out. All right, so this is what you can get by graphing. Then what you'd want to do is look at the prospective zeros. By rational zeros theorem. Rational zeros theorem says that x could be any plus or minus. Take the factors of the last term, so 1, 2, 4, and 8, and put them over the factors of the first term, 45. So 1, 3, 5, 9, 15, and 45. Those are all the possible combinations you can get. Now, -4 seemed pretty obvious, and we do have a 4 here divided by 1 will get us a potentially -4. So, in order to do this by proving zeros by factorization, you are supposed to do some sort of division. So it's up to you. Do you want to do synthetic? Do you want to do long division? I do synthetic. It's faster. It's easier. All right, so we're going to divide negative 4 into 45, 192, 41, negative 30, negative 8. So 45 comes down. We multiply by negative 4, which ends up being a negative 180. Add, this is 12. Multiply by negative 4, we get a negative 48, makes a negative 7. Multiply by negative 4 gets a 28, add gets a negative 2, multiply gets you a positive 8, add gets you a 0. This is telling us that when we take 45x to the fourth, 192x to the third, 41x squared, minus 30x minus 8, oops, and divide by x plus 4, because that's what this term really is. This is x equals negative 4, which is x plus 4 equals 0. When we divide this term, x plus 4, into this polynomial here, we end up with 45x to the third plus 12x squared minus 7x minus 2 with 0 remaining. Now here's the other great thing. You do not have to go all the way back to the beginning of this and then try something else. You can, now that you have something with a 0 remainder, you can start here. You factored this out. Congratulations. Right? This is x plus 4 times 45x cubed plus 12x squared minus 7x minus 2. You've earned that. Don't let it slip. Don't go any further backwards. So now we want to take these other possible fractions and see what we can get. Now, one of the quick ways to do this is you say, well, I think it was negative a half, so let's plug it in. y1 of negative 0.5 is negative 3.9375. So clearly it's not that. So what other negative values can we get that's reasonably close to negative a half, but a little bit closer to 0? So we've got like 4/9. Negative 4/9 gets us a negative 1.668. So again, we're getting really close. So that's a negative 0.44, give or take. So let's try negative 1/3. And that's where we get a 0. The other option would be you go into your zeros function. Go into your zeros function, look for the 0 at this particular point, but you are not allowed to use that for your exam and just say, ta-da, there it is. You have to go through this and prove that, yeah, that is actually going to work. So we're going to do negative 1/3, which on the calculator gave me a 0. The question is it actually a 0, or is it just really, really close to a negative 1/3? Yeah, this is going to be 45. Times negative 1/3 is going to be a negative 15. Add is negative 3. Multiply is going to be a 1. Add is a negative 6. Multiply is a 2. And add is a 0. So this one's going to work for us. Give me 1 second here. All right. So now what we've got here is a x plus 4 from before. And then we've also just factored out x plus 1/3. And now what we've got left is a 45x squared minus 3x minus 6. Now if you notice something about all these terms, all of them are divisible by 3. So we can actually factor out a 3 as well, and we can get rid of the fraction here. So x plus 4 times x plus 1/3 times 3 times 15x squared minus x minus 2. Factor out the 3 from this stuff, put it out front, and now we can give it to this one instead. So x plus 4 times 3x plus 1 times 15x squared minus x minus 2. Now from here, we can also do the AC method for this one. This is going to be a negative 30, a 15 and a negative 2 multiplied together. Well, 30, when our signs are opposite, have a difference of negative 1 if we have values that are, again, 5 and 6. The bigger one is negative. They have opposite signs, so the smaller one must be positive. This is going to get us a negative 1 when we add them together. So this is going to split. This is 15x squared plus 5x minus 6x minus 2. 5x from each of these. It's going to be 3x plus 1 minus 2 times 3x plus 1. So we get an extra 3x plus 1 term and a 5x minus 2 term. This is 5 halves, or nope, this is a 2/5 or a 0.4. So again, that was about what we had before. All right, somewhere between a third and a half. 0.4 fits that bill. And then we got the 3x plus 1 that we already had up above, and the x plus 4 that we already had up above. So, factorize. We get these four things. So this is x equals negative 4, x equals negative 1/3, and x equals 2/5, where negative 1/3 has a multiplicity of 2, and negative 4 and 2/5 have a multiplicity of 1. Right, those are the zeros, and just as a caveat, right, this has that multiplicity. Works out pretty nice. All right, 3 more. All right, number 10, solve. With exact solutions on theta going from 0 inclusive to 2 pi exclusive. So we have 4 sine squared theta minus 8 sine theta equals 5. This is a trap. Do not factor the sine of theta out from the left-hand side and then just figure out, oh, I'm just going to get this and multiply them together and get 5, because that's not going to happen. Right? You are not going to find 2 factors of 5 which are going to work out nicely for this. It's just not going to work. So, what do you have to do? Oh, look, it's a quadratic. Do the AC method. So, 4 sine squared theta minus 8 sine of theta minus 5 equals 0. I did this on purpose, right? Students fall into this trap all the time, and I tell them explicitly, do not fall into this trap. Alright, so one way to deal with this, if you don't like how it looks, use algebra. Let the sine of theta be equal to A. So here I've got 4a squared minus 8a minus 5 equals 0. Well, that makes it a bit more manageable for those of you who don't particularly like having trig functions in the middle of your algebra. So how do you do the AC method in this particular case? Right, this is going to be, again, a negative 20. We want factors that have opposite signs and bigger ones negative, and we need 8 out of them. So 1 and 20, 2 and 10, 4 and 5. You probably already see where this is going. Bigger ones negative, smaller ones are positive. Only ones that get you negative 8 are 2 and negative 10. So 4a squared plus 2a minus 10a minus 5 equals 0. 2a is factored out here, a plus 1. Minus 5 parentheses. Yeah, did I just, yeah, okay, I'm fine. No, 2a, there we go. 2a plus 1. That was my problem. So then here, factored out a negative 5 from negative 10, and we get a positive 2a. Negative 5 from negative 5 is a positive 1. So 2a minus 5 times 2a plus 1 equals 0. And then in this particular case, set each of them individually equal to 0. Two a equals 5, or 2a equals negative 1. A equals 5 halves, or a equals negative 1 half. Well, this is the sine of theta equals 5 halves, or sine of theta equals negative 1 half. Sine of theta cannot be greater than 1. So that whole line of questioning is moot. Get rid of it. Then here we want the sine of theta when it equals negative 1 half, which again, if you look at the unit circle, negative a half is like here, and sine value gets you the gets the vertical value. So it's negative a half, which is going to get us out to this point here, and this point here. This creates a 30, 60, 90 triangle. Your reference angles are 30-degree angles. So if you take the inverse sine of both sides, you get that theta is going to be the inverse sine of negative 1 half, and also pi minus that. The 30-degree reference angle is a negative pi over 6, and pi minus negative pi over 6. Negative pi over 6, we're going to add 2 pi. Which is 12 pi over 6, minus 1 pi over 6 is going to be 11 pi over 6. Or pi minus negative pi over 6 is going to be adding. Pi plus pi over 6 is going to be 7 pi over 6. So 7 pi over 6, 11 pi over 6 are the two answers we're going to get for this particular setup. All right, 11. Find all complex roots of this polynomial. This is a complex valued polynomial. It is no longer a real valued polynomial. So you're not able to just say, oh, take the fifth root and be done with it. Matthew, if you're here, this is what I was trying to talk to you about, although, this might be above your particular pay grade, so it's fine. Don't worry about it too much. But the fundamental theorem of algebra says that for any nth degree polynomial, there are n complex solutions. So there are 5 solutions to this 5th degree polynomial in the complex plane. What are they? Well, the easiest way to do this is to say we're going to take these here, -1 plus I times root 3, and convert this into polar form. Currently, this is rectangular form, which is a plus I times b times I, or x plus iy, or any of those random things that you can come up with. So in polar, what we want then is this to be r times the quantity, the cosine of theta, plus I times the sine of theta, or r times cis theta. So how do we do this? We'll figure out where this is first. So in terms of rectangular coordinates, we have a -1 is our x direction, our real values, which again is termed excessively poorly, but nonetheless. So real values this way, imaginary values this way. -1 plus root 3 times I. This gets you this particular vector out in space. We need to find r here, and we need to find theta here. I've already told you before, this theta prime is going to be our reference angle. And the r value is kind of trivial once you know the Pythagorean theorem, and this is your x and this is your y. Right, so r is equal to the square root of -1 squared plus square root of 3 squared. So r equals the square root of 1 plus root 3 squared is just going to be 3. R equals the square root of 4, which is 2. So r equals 2, which you would also know if you know your 30, 60, 90 triangles. That being said, right, this is going to be a 60-degree angle in the second quadrant because of our reference angles that we can find. So there are 2 ways to do this. Either you can say the tangent of theta is going to be equal to y over x, which is going to be a negative root 3, and then theta is the inverse tangent of negative root 3 in quadrant 2. Inverse tangent of negative root 3 is going to be a 60-degree reference angle in the 4th quadrant. So your theta from your calculator would actually be negative 60 degrees. So here, what we do is add 180 degrees to it. Again, this is quadrant 4. And when we add 180 degrees to it, we're going to put it back into quadrant 2. So theta is equal to a 120 degree angle, and r is 2. So -1 plus I root 3 is going to be equal to 2 times the quantity, cosine of 120 degrees, plus I times the sine of 120 degrees. So this is what we get first. Then this replaces all this stuff up here. So this is going to be x to the 5th is equal to 2 cis 120 degrees. But here's the thing. It's not just 120 degrees. It is, in fact, any coterminal angle to 120 degrees. So we can add 360 degree k onto this and say it could be 120 degrees or any full rotation on top of that. Which means that x can be 2 cis parentheses 120 degrees plus 360 degrees k raised to the 1/5 power. This is going to be 2 raised to the 1/5 power times the cis of, using de Moivre's theorem, the cis of 120 plus 360 degrees k, all raised to the 1/5 power, allows this to come in as a multiplier on the inside of this function. There are several reasons for that. We can go over de Moivre's rule some other day. This is mostly just for those of you who have already taken precalculus. So 120 degrees k plus 360 degrees k. Nope, 120 degrees plus 360 degrees k times 1/5. So 2 to the 1/5, 5th root of 2, times the cis of 120 divided by 5 is going to be 20, 2 left over 4. Should have known. All right. 24 degrees plus 360 divided by 5 is 72 degrees K. These are our solutions. X is going to be equal to all of this when K is equal to 0, 1, 2, 3, or 4. Now, why that is broken down further in what we get when we actually do it out. So it's 2 to the 1/5 times the cis of 24 degrees. 2 to the 1/5. Cis of 24 plus 72 is going to be a 96 degrees. 2 to the 1/5 times cis of 96 plus 72 is 168. 2 to the 1/5 cis of 168 plus 72 is going to be 240 degrees. So one nice one at least. And 2 to the 1/5 times the cis of 240 plus 72 is going to be 312. Why do we stop there? Well, if we went one further, 312 plus another 72 is going to bring us to 384, which coterminal, subtract 360, gets you back to 24 degrees. So it's exactly the same if you did 2 to the 1/5. Oops. Cis of 384 degrees. Right, this is just the same as that one. This ends up creating a cycle. So it goes through these 5 answers every single time. All right, and these are the answers in polar form. If you want the answers in rectangular form, then you have to undo all of this stuff by actually plugging it into your calculator. The 240 is an easy one that you can do. So you end up with 2 to the 1/5. This is 240 is equal to 2 to the 1/5 times the cosine of 240 plus I sine 240. All right, 240 degrees is a 60-degree reference angle in quadrant 3. So this is going to be -1, -√3, and +2 for our 3 sides to the triangle. Our reference angle is here. So the cosine is going to be short side -1/2. So 2 to the 1/5 times -1/2. And then here the sine of 240 is going to be -√3 over 2. So let's do a minus 2 to the 1/5 times √3 over 2. So you'd actually want to plug those in. All right. That one I got a 6 pointer for. Again, setting up in polar forms, probably 2. Doing the correct de Moivre's theorem is going to be another 2, and then your answers are going to be another 2. 12. All right, convert to rectangular form. R equals -7 divided by 5 cosine theta plus sine theta minus 2. All right, the things that you have between polar and rectangular form are going to be our r squared equals x squared plus y squared bit that we've done before. You've also got r cosine theta is equal to x, and r sine theta is equal to y. Those are going to come in handy. Do not mix variables when you're doing this. I've told you this before, I'm sure. Do not mix up your variables and put them together. I'm going to recommend that this term here just get multiplied over to the other side. So this is r times the quantity, 5 cosine of theta plus sine of theta minus 2 is equal to -7. That's easy enough. Multiply this in. This is going to be a 5 r cosine theta. Oh, would you look at that? There's an x. So 5 times x plus, this is going to be r times the sine of theta. So there's a y. And here is a minus 2r. This is minus 2, but then r could be found from this one up here. R squared is equal to x squared plus y squared, so therefore r is going to be equal to the square root of all that. Square root of x squared plus y squared equals -7. And quite frankly, I would have my students stop there. You don't need to try to solve for y. That's crazy. Why would you do that? Right, the problem with it is that there are 2 terms with y's in them. If you try to square anything to get rid of the square root, you're just going to end up with a bigger mess than what you started with. So, you know, yeah, sure, in theory you could find it, but I don't care. This is fine. You could plug this into Desmos, and again, get some sort of graph. All right, this is a 4-pointer. Basically, I'm doing like 2 or 3 points for all the conversions and 1 point for work. Since it's such a condensed problem. All right, cool. So this has been the final exam for my pre-calculus class. It gets kind of interesting sometimes. Anyway, I am going to grab a drink and refill water, cycle water, all that good stuff. And I will be back. We will change the stream name and get over to Elite Dangerous. So, see you in a few minutes. I will be right back.